welcome everybody to week 7, day 2. Today we're going to be talking about the difference between vectors and arrays. Move.cc. And we're going to be doing a little bit of sorting today as well. So, one question that I get a lot asked is, what's the difference between a vector, like if I want to make 100 integers, what's the difference between a vector events named vec size 100 and this integer array 100? Simple answer. This is what you should be using. This is what you should not be using. Okay? Controversial, I'm sure, but there's actually no benefit to doing it this way. This is how it was done back in the C days, and if you're writing C, that's fine. Do it, you know, make a C-style array. Okay? This is called a C-style array. Use it if you're writing C. Okay, that's the only answer that I can have for you. This is a vector. But we'll talk about the pros and cons of the two different approaches. And spoiler alert, vectors are all pros and C-style arrays are all cons, with some very few exceptions where there's also something called the array class. Here, array of integers of size 100. And probably we should not use magic numbers, but whatever. C++ style array, this is called, okay? This is, if you really need an array, I guess, use this. But you're not going to. This right here is what you should be using for the whole semester. Okay? You'll see people online using that all the time, and I don't know what percentage of them are doing bad code, like actual buggy code as the result of it, but the answer is a lot of them. If you stick to the guidelines that I give you for this class, which is to use vectors and to use .at instead of square brackets, then your code will literally never go out of bounds. So, first of all, let's talk about what it means to go out of bounds. So if we were to initialize these values here, so the 40, 10, 30, 50, 6. This works fine. Oh, except we can't give it a size anymore. Okay. So if you want to make a vector with no size, and we'll talk more about vectors with no size on Friday, you can do it this way, and this will figure out the size of the vector from the curly braces. The curly braces are called an initializer list. In general, using curly braces to initialize things in C++, it's called universal initialization syntax, and you'll see this all over the place. In the previous class, some students tried doing this with smooth parentheses, and smooth parentheses are wrong. It's not a smooth parentheses, it is a curly boy. Okay? So, let's just show you guys how bad going out of bounds is. And so, these three bits of code here are, on the surface, exactly the same. We're making 5 integers, and we're initializing the first variable in each of these collections of integers. We're setting the first one to 40, the second one to 10, the third one to 30, fourth one to 50, and the last one to 6. Okay, so if I wanted to write a for loop to print them all out, I could do it like this, right? So for each element in vec, see out that element. Okay, and in fact, this works with R and R2 as well. Okay, let's just put a little divider between each one, I guess. see it. And if we compile the code, you'll see that we're getting 42. Yep, looks exactly the same. Are you all with me so far? We're doing code to print a container of integers. Oh, can you guys hear me? Microphone on? 19 people watching the stream? Okay. So does this for loop make sense to you all? Do you understand that it's basically the same thing as this for loop for size I equals 0, I is less than vector dot size, I plus plus, see out vector dot at. So that and that are exactly the same. We use typically a full for loop like this, either when we need to like go over like maybe half the vector, so we could do something like that and just print the first half, or if the index matters. And so if you need to actually get the index of things, then we would use like a full for loop like this. But a range-based for loop, I use if you're going to do something on every element of a vector, the range-based for loop is just the right tool for the job. It's safer. You don't have any indexes, and so an index is like which part of the vector you're in. And so if you have 5 elements in the vector like you have here, the indices go from 0 to 4. And there's some really tricky bugs you can get, like if you put a +1 in there, right? I want to print, you know, if I'm on I equals 0, I want to print element I. What's going to happen though when this gets to the end of the loop? The very last time I will be 4. 4 is less than 5. It then tries to access I dot out, a vector dot at 4 plus 1, which is 5. What happens if you try accessing element 5 in a vector of size 5? What does the dot at function do? It's attempting to go out of bounds, but does dot at allow you to go out of bounds? The answer is no. Yeah, so size t is just an unsigned integer, and I put size t in there because comparing signed and unsigned integers will give you a warning. But in general, it's bad practice to compare a signed and unsigned integer, just due to the way they convert between each other. So yeah, it crashes, but it crashes nicely. Now let me show you what would happen if rather than using dot at, I wrote this code using square brackets. This is the same thing as vector dot at, all right? Except it does not do bounds checking. Okay, so it's just going to print what? What is this going to print? Cow? Maybe. It'll print whatever's in RAM. It's just going to print whatever's in RAM there. So a 0, I guess. What if we did this? What if we went even further? What if we printed out the first 100 elements of vec? What's that going to print? Bunch of zeros? What do you think? I'm not using dot at. If I use dot at, it would kill the program. You'd be like, you went out of bounds. Don't do that. No, don't do that. What if we did this? What's it going to print? You really want to see something other than 0? Let's find out. I actually don't know. This is undefined behavior. Yep, we got some numbers that aren't zeros. So, something there. Don't know what it is. Something. We're just printing the contents of RAM. So we're just going through RAM, just printing things. You know, as you do. This is why it's so dangerous. And people underestimate just how powerfully bad out of bounds memory accesses are. They're really, really, really bad. Because I'm just printing these and that's, I guess, okay. Can it crash your code? Sure, it can actually. If you go too far, if you're like the dwarves of Moria and you dig too deep, you can, in fact, crash. Because your program has certain boundaries set up called segments. And if you ever access memory outside of that segment that wasn't allocated to you, the operating system knows, no, you're not supposed to be there, and it kills your program. So what do the square brackets mean? This is exactly the same as writing vector.at I plus 1, except no bounds checking. And you will see a lot of people online using these square brackets, and if you ever see that, run away, okay? Because there's no bounds checking. You should always, especially when you are in C-Sci 40, you should always do bounds checking, because downside, it slows your program down. Kind of substantially sometimes. It can. Upside, if you ever go out of bounds, you will not know it if you use square brackets. You absolutely positively should always be using vector.at in first semester computer science, because you will make mistakes. Not like me, I don't make any programming mistakes. I just, I just write perfect code the first time, every time. But, but the square brackets are unsafe and faster, okay? So if you're working for a financial services company and you need to squeeze every microsecond of performance out of your program, and you've run it with .at and it's in bounds, you've tested it thoroughly, I give you permission to put square brackets there. But you will see people just using them by default because they don't know any better, and they will go out of bounds all the damn bloody time. And this is really, really, really bad. Reading is somewhat bad, but if you're writing to it, like if you're trying to like increment the value of every element in this vector, you are now changing the value of RAM that you don't own. I mean, it's technically owned by you, the user, but like somewhere in RAM, there could just be like your social security number. Guess what? Your social security number is 1 higher now. What? I never changed my social security number. Yeah, you did. You did so because you were dumb and you used square brackets. And these are the kinds of bugs that are so hard to find out and solve, because like you've got like, you got like your int social security number in here, and my social number is that, obviously. And then like at the bottom here, like you see out your social security number, and it's not that. It's like, you're like, what? I never changed it. Nowhere within my code did I change my social security number, but it's changing. And it's like, yeah, it's because you're going out of bounds. Do you know how fiendishly hard this is to track down? When you don't have any code modifying SSN and SSN is changing, that's the kind of thing that like causes programmers to like rip their hair out. Like, this bald spot here, right, is from it's from trying to solve out of bounds problems. And people like just still use square brackets, like as if it's like not a major concern, as if it's not the source of more hacking incidents than anything, right? Because people go out of bounds, and then when you read a packet from the internet and just put it into an array, and that array you're just writing things into the array, it's like, all right, well, the person over the internet now is going to type in a new password, and it's going to overwrite the password to the server because I'm just writing to RAM. Like it's a real big pet peeve for me, because people are like, but what about the speed? Yeah, so you're going to be corrupting memory faster. Corruption of memory, which is what this is doing. This is going to be overwriting things in RAM. If I run this, it's going to be just changing random things, and all those spots in memory that were zeros before, they're ones now. Hope that wasn't important. Hope you weren't using that to hold your bank account information. And the worst part is these things can happen only some of the time. Yeah. Like your code might actually work right 99% of the time, and then some of the time you just happen to overwrite, like, I don't know, something holding like the size of the vector. Now the size of the vector is 1 too high, and if you don't bounds check your array, you're going to have a bad time. That's exactly right. That's exactly right. We should make this pin that to the Discord channel. This is absolutely true. Okay. So, it's an open question as to why people still recommend using square brackets. Speed is not as important as safety, in my opinion. But people will disagree with that. It's like, no, you need it to be fast. Okay, fine. Write it fast after you've proven it's correct. Because like in the previous class, I just pulled up a random website. I just searched for, make me an array of Fibonacci numbers. Okay, cool. I come down here and square bracket array. And I'm like, ooh, uninitialized variables. Ooh, this is not going to be good. This is not going to be good. Okay. So, without barely even looking, I'm like, this is going to be corrupting memory. Good job, easycodebook.com. You're now corrupting RAM. You're overwriting people's bank accounts. You got hacked. Well done. You know, I'm sure that was worth the speed increase of not using .at. So, come back to this gem of a program here. So, don't use square brackets. In this class, I don't want to see square brackets ever happen. And if we try going out of bounds, because you can try going out of bounds with .at, you know, if you try going out of bounds, then what happens is, rather than seg faulting and crashing, the thing detects it. It's like, nope, you tried accessing memory outside of your bounds. It gives you a nice error message. You tried accessing element 5, which is greater than or equal to the size of the vector, which is 5. Because remember, it's 0 to 4. So you tried accessing element 5. There is no element 5. Crash. Okay? And you might be like, but it's the same thing. Remember how it didn't crash some of the time with the square brackets? Remember how it was allowing you to just read and write to RAM just in memory somewhere? Just going and corrupting memory? Yeah, don't use square brackets. Okay. Yeah, so being able to get the size of the vector is nice because it lends itself well to a for loop like that. But yeah, sometimes you do a full for loop just because you want to say like index I, something like that. Like sometimes you want to just print, you know, what index things are at, and that's fine. You don't always have to use a range-based for loop. I use both. It just depends what I need. If I need to know the index, you know, the location of each of the elements, then I use a regular for loop. If I just care about the values, I use a range-based for loop. Okay. So, the first time through this loop here, x is going to be 40. The next time through the loop, x is going to be 10. Next time through the loop, x is going to be 30. So this range-based for loop is going to set x to each of the values in the vector. This is different from a regular for loop. Rather than the values of the vector, it's the indices of the vector. So the first time through the loop, I is 0. 0 is the index of 40. Next time through the loop, I is 1, which is the index of 10. And so you have to go from the index to the value by using this. You notice how here we don't use vector.at at all. So it's safer. A range-based for loop is safer because you can't go out of bounds. It's safe. Same speed, less typing. But if you need the index, which you do sometimes, then use a regular one. Do you guys understand the difference between the two? They're kind of equivalent, and you can probably hack something together. Like you could see like int I equals 0, and you could do like cout index I plus plus. Like you do something like that, and then, you know, kind of slap the index on top of the range-based for loop. But kind of once you're at this point of having the I equals 0 and the I plus plus, you're kind of, you know, you're kind of mostly writing a for loop anyway, so a regular for loop anyway. Okay, so difference between vectors and arrays. Pros. Use the learning point for today. Learning point for today. Pros, cons, vectors versus arrays. Okay, so vectors are slightly slower than arrays. It's arguable if you'll ever notice the speed difference. Arrays are limited to about 100 megabytes. Vectors about 2 gigabytes, maybe more, depends. I'll just say unlimited. Vectors printed by RAM. Okay. So yeah, it's faster to use an array, but if you're only doing small arrays, yeah, probably not. And that's only to create, it's not to access. If you're like creating a lot of vectors versus creating a lot of arrays, use an array, but use a C++ style array. But for this class, just use vectors. Just use vectors. This will not matter. The speed difference does not matter for this class. Okay. Vectors have dot size. C-style arrays do not have dot size. That's huge. Because you want to know how big your array is so you don't go off the end of it. Right? When you do a for loop like this, you want to know how many elements are in the vector. How many elements are in this array? Like if I wanted to rewrite this so that I'm using a regular for loop for int I equals 0. Get rid of this, I guess. Let's rewrite that range-based for loop for int I equals 0. I is less than r dot size. Nope, that doesn't exist. That does not exist. Cout r I. That doesn't exist. There isn't one. Can't tell the size. Yeah, there's a way of kind of hacking around it. You could do this, the ending of it minus the beginning of it, like that, and that should do it. It's really hacky though to do that. In general, what people do with arrays is they have to do this. Size t size is equal to 5. So downside, you have to track it. You have to track the size separately in a separate variable and hope that you don't get confused. So then rather than doing that kind of hackish nonsense there, we do this. For int I equals 0, I is less than size I plus plus. Okay. And again, you don't have .r either, so you want to be very, very careful that you are not going out of bounds. For something simple like this, I'm confident I'm not going out of bounds. My spacebar is extra loud today. Sorry. Just whacking it for emphasis. Can't tell the size. That's how Zybooks was doing it. Yeah, it's kind of hacky though, and it only works in the original scope in which you declare the array. If you pass that, we're going to show passing these things to functions in a second. But if you pass an array to a function, then you lose the size at all. So you basically have to do this kind of no matter what. And that actually is not a good. It's not good when you have to have two variables that have to be kind of kept synced up with each other, and like hope that they're the same, and hope they don't get modified accidentally, and hope that you're passing the right ones together. Like if you're copying and pasting a bunch of arrays around, you might paste the size for the wrong array, right? And now you go out of bounds. It's much, much better to have this member function right here. So you can just query when you're looping over a container, just tell me how big you are. And the good news is this actually works with C++ style arrays. And that's why I'm saying if you absolutely have to use a C style array, which you don't, but if you did, like you're working for financial services or something, and they're like, we need maximum speed, use a C++ style array instead. It is 100% better than a C style array. All upside, no downside. Vectors are, I would also say, are basically better than C style arrays. All upside. The downside is a very small speed cost. And since arrays have to be small, you know, you could I would say it's like 99% vectors, 1% use arrays. It's just a general rule of thumb. 99% of the time you should use a vector. A very small amount of the time you should use an array, but not this array. Not this one ever. Never. You should never use this one. If you absolutely need to use an array, use this. The C++ style array is just better. If you want to use a C style array because you're writing C, fine. If you're programming in the C programming language, knock yourself out. That's fine. Yeah. And there's probably some sort of argument you can make that like code dense, like once you get into like C-sci 45, there might be like a code density argument that could be made about C++ style arrays to cause more cache misses or something. Once you get to that level, there's like a 0.01% chance that I might give you permission to use a C style array. But you would have to do a lot of benchmarks to convince me of that. So in general, vectors, this is what you should be using. Here you go. 99% of the time. C style arrays are like a 1%. Okay. And in this class, you should never use a C style array, ever. Never use square brackets either. Even though there's a speed advantage, don't do it. Okay. So vectors and C++ arrays have dot size. Oh, I already said that. Dang. C style arrays don't, so you have to track. Vectors in C++ arrays have .ack, which do bounds checking. C arrays don't. Every time you access a C array, you've got to be damn sure you're not going out of memory. And what happens is that because it's kind of a pain to track that and have an if statement all over the place, is that a lot of programmers just don't. And that's how they get hacked. That's how they get memory corruption. That's how they get random crashes, because they're just too lazy to do it properly. Okay, so let's look at, on that note, let's look at this Fibonacci thing that I pulled up in the previous class. Again, I didn't, have this ready in advance. I literally Googled it in the previous class. You can see the recording on it. So let's go through this. And let's see if you guys can find the problems with this code. So right off the bat, this is Windows. That's a problem. No, it's not. I'm being sarcastic now. That's it's a Windows thing. You don't need to worry about that. This. There are 3 problems in the 3 variables that are being created here. What are the problems? There's 4 problems with the 3 variables being created here, which lists some problems for me. Let's do a code review. Okay. A code review is when you go through somebody's code and you tear it apart. And if it's in person, I do so in a very gentle and positive fashion. If it's somebody online who's teaching young Padawan programmers to code improperly, I'm going to be a little bit more pissed at them, because easycodebook.com, y'all should have known better than to do this. Okay, array isn't an int. Actually, this is actually fine. And I learned something really cool the other day, which is this. Int R100, that's fine. That's how you declare an array of 100 R's, and an X, and a Y. And Mr. Bell, you here? Watch this. That. Let's see. Yeah. That's a forward declared function. So if I have a thing down here called int foo int x return x plus 10, this is for declaring it. So you can see out foo of 42, and this will compile because I have forward declared this function to exist. Wait, what? Yeah, I know, that was my reaction, because I've been doing this for like a long time. And I was like, what's up, Juarez? Yeah, you got to see this, Juarez. This is like some mind-blowing stuff right here. I'm sorry, it's just terrible. This is from the Kernighan and Ritchie C programming language book. I was actually flipping through it to see if I could learn something new, and I flipped it randomly to an open page, and I learned that, and I was like, excuse me, what? Yeah, so you can declare an array and a variable, I knew that, and forward declare a function that returns an integer all on the same line. So, yeah. Yeah. For those of you that don't know why this is so horrible, normally you don't ever forward declare a function like that. Normally, we just put the functions either above main, but here it's not going to compile because we're calling a function that it's never heard of. So normally, as I'm sure you guys have learned, you have to do something like this: int foo, taking an x, semicolon. And this forward declares a function. But you can actually do it with variable declarations. That's yeah, that's legal. So you'd forward declare a bunch of functions on one line, yeah. And it's also scoped, like this is only inside of main, right? So it's only forward declared for main. I don't know why you'd want to do that, but there you go. What was that book? So Bjørn Strustrup, author of C++, said that this book is sort of the definitive guide to how you should write technical documentation. And it's actually pretty good. It's actually a really good book. And it goes through the entire C language. You can see the C language is not that big. It's got plenty of source code, plenty of examples. This part's all reference manual, so it's got data structures. Like, it's got pretty much everything you need. If you want to be a C programmer, you can just read this book, and there you go. You're a C programmer now. Take you a couple days. C++, the standard for the C++. It's like a stack of books that go up to the moon or something. So, yeah. So let's go back. So, sorry, that's a aside. We're doing code review. So, now that you guys have had time to think about this, what's the problem? There's 4 problems here. There's 4 problems with this. Otal did not initialize some of the variables. True. Yeah, it's not going to cause any bugs, but that's 2 of the problems. I should be initialized, in should be initialized. Just yesterday, I was helping a person on Reddit, and they didn't initialize their variables, and they initialized the variable within a for loop, but the for loop didn't have to run because it was something like this, right? So if they had typed in a negative number or something like that, it would never initialize their variable. Then all sorts of hell would break loose. So if the user had typed in like -5 or whatever for their code, it wouldn't have initialized. And so that's why I say you just need to get into the habit of always initializing your variables, always. Just because you think it'll be fine, but like this whole time, like you're just kind of cruising through here. I is not initialized during any of this time. If you try outing all of the things, you're going to have an uninitialized I when you see it out. Okay. So, come on. You found 2 of the 4 problems on one line, on the first line. Give me 2 more. What is that? What is that thing that I'm looking at there? No brackets in the for loop? It's fine. Brackets, the indentation here is kind of garbage. But you don't need brackets, technically, if you have a one-liner. So, brackets are optional if you have one line following a for loop or an if statement, or a while loop or something like that. 100 is too many. Oh, interesting. It might be, actually. But when does Fibonacci overflow? I don't remember off the top of my head. It might actually be too many. Okay, so magic number. Yes, very good, Portnoff. So, why 100? Why 100? We're not making 100 Fibonacci numbers. Why is array 100? Why did you pick 100? Why not 10? Why not 50? Why not 1,000? What's the meaning of 100 here? You know, there isn't one. So they just write down 100. This should be a constant. And it must absolutely, positively should be a constant because it's the size of the array. And remember how I said with arrays, you have to track it separately. You have to make a variable like this that holds the size of your array. Because if you don't, you're gonna have a bad time. And it's something that is even more annoying because you could like add another number here, and every time you add a number there, you got to change the number here as well and hope you don't forget. And even worse, if you delete something out, now you're gonna buffer overflow because you're gonna be accessing the first 6 elements out of R when there's only 5. It's kind of a garbage system, but at least I did it, right? At least I have it. This is the proper C way of doing things. They did nothing. This, once we get past this line, we have no idea how big R is. Okay. Nowhere within this code does it actually refer to the size of the array after it. Okay, so we see out the number of Fibonacci terms required. We see in that, which is n. Okay, criticism here. What should they do next? They have just asked the user for an integer. They should vet the code. They should vet the input with the code. What kinds of things should they check for? You can think of at least 3 things they should be checking for. If it's on an integer, good. What if they typed in grease? What if they typed in squirrel? Right? Any future CN statements would fail past that point. This is a small program. There's no other CN statements. It'll be fine, but they're not checking for it. Not lethal. It's going to leave n as 0 probably. But they should check for it definitely. Negative numbers. Yeah, absolutely. Absolutely negative numbers. Yep, absolutely. And especially since they're assuming, like, look at this. Like, they're assuming there's going to be at least 2, right? If they type in, give me 0 Fibonacci numbers, if they're doing it correctly and setting the size of the array based on the n typed in, this would be a buffer overflow. But fortunately, they did it wrong, so they're always having 100 numbers, so this won't buffer overflow. There always will be a 0 and a 1. Yay, good job, I guess, by accident. But it's still needless work. Like, if you're asking for 0 Fibonacci numbers, there's no reason to compute 2 of them, right? So, yeah, so n should be at least 2, probably, I would say. And what's the maximum? Because that's the big one. What would happen if we typed in a 200 here? I want you to create 200 Fibonacci numbers and store them into this array of size 100. What's going to happen? It's like, you know, when you see like a car on like an icy hill and they're braking and you see the tires are like trying to stop and like, but it's starting to slide down the hill. I think you guys know it's coming. I've been there, by the way, in North Dakota. It's a terrifying thing, by the way, to be sliding down a hill out of control. People were used to it. People going right through a red light, just ice skating down a hill. People in the town were used to it. They just waved me through, and I went, shh. Yep. This is a car crash waiting to happen because they did not vet their input. They should have checked to see if CN was invalid. They should have checked to make sure N was at least 2, because they seem to be assuming there's at least 2 here. Those are minor issues. The big issue is they don't check to see if N is bigger than 100. Right? Because this for loop here, you guys see what the problem is? What if N is 1,000? How many elements of R is it going to write to? It's going to be reading from them and writing to them. How many elements of R, maybe this is a trick question, how many elements of the array are they going to be reading and writing to? If they type in 1,000 for N. 100, very good. You did not fall for my trick question. Yeah, R's got 100 elements. It's going to read and write to all 100 of them. And then the next 900 are going to be variables in RAM somewhere. And it's going to read and write to 900 of them. And if you had, you know, things in there like, I don't know, important bank account information, things like that, they're all gone now. They're all Fibonacci numbers now. Congratulations, you have now wiped out your RAM and filled all the variables you had in your program with Fibonacci numbers. You know, you go to hit somebody with a sword and it's like Fibonacci 500, you know, and So, but you would kill the monster, except the monster is at health Fibonacci 800. You're just like, what the hell is going on here? Why is my name a Fibonacci number? Why is my magic spell mana count a Fibonacci number? Everything's a Fibonacci number now. Yay. Is it possible to overwrite the array on purpose? You mean overflow the array on purpose? Writing to an array, you can, like, this would be fine. This code would be fine if they had vetted in, right? If they had vetted in, this would have stayed within bounds. The code would have been fine. But the second I see them use square brackets and this, like, there's just immediately the sense of foreboding, the sense of, like, doom, impending doom. Like, did they bounds check properly? And, like, a lot of the time, the answer is no. A lot of the time, the answer is no, they did not bounds check properly, and this is going to clobber things in memory. And the worst thing is the code will appear to work correctly. The worst thing is they run this code, it prints out the first 200 Fibonacci terms, and it works fine. Because, you know, that thing that was your social security number before, it's now Fibonacci 150, and when we go to print it out, it's going to print out Fibonacci 150. It looks fine. You've left the place a desolate wasteland. Yeah, that's a good one there. That's actually a great example of what's happening inside of your computer's RAM. And then this is actually what the programmer of that thing is saying. This is fine. It worked. It works. It works. Unless you do so many, you segfault and then it crashes. But yeah. So yeah. He's got a trailing comma too. Process 55 seconds to run that. 55 seconds. How slow is your machine? 55 seconds. Man, easy code book. I take back everything you say. You clearly need the advertising revenue so that it doesn't take you like 5 seconds per number to do an arithmetic. I'm sorry. I mean, that's probably including the compiling time, but my lord, this is not a big program to compile either. Okay. This is a brutally painful experience for me to look at. And if I were to rewrite this using like vectors, it would be using .ats and bounds checking and things like that. So, yeah, if you don't bounds check your array, you're gonna have a bad time. Good. All right, so let's pass these things to functions. Let's see what that looks like. Let's compare and contrast. Okay, so let's make a function that is going to count elements less than 100 or something, and vector of x. So let me make a function that takes a vector, and it's taking a vector by value right now, which we'll come back to. But I just want to do something like this. I just want to count how many elements are less than 100. So I could say for every member of the vector, if that member is less than 100, add 1 to my count, and return the count. Okay. And we'll need to maybe make some of these bigger. They're not all under 100. Okay. And yeah. See out the number of elements in vec less than 100 are so there's 2 elements less than 100 in there. Okay, so the code works. Now let's talk about it. First of all, when we do call by value, are we passing in the reference? Are we passing in other words, the memory address, the reference? Are we passing the memory address of vec back in main? Or are we passing in the values of vec? When we do call by value, do we pass in a reference? Or do we pass in the values? When we do this, we're passing the values. We're duplicating, well, technically it is passing in a memory address, but it is going to duplicate all of the values in the vector. Okay? So it is going to duplicate vec, and if we had 1,000 things in vec, this would be a very expensive operation. It would be unnecessarily making a clone of vec and then counting how many of the clone is less than 100, then it destroys the clone. And that there's no reason to do that. So what should, this will clone, call by value, clones vec. For 5 elements like this, you're not going to notice anything. Works fine, but it's technically a clone. We're counting how many are less than 100 in the clone. What should we change this to? So that we pass in the original without duplicating it. Yes, const reference is exactly right. So passing it by reference will pass in the memory address of vec, and then that's just a single thing you have to pass in without duplicating. It's nice. And since we're not changing anything, right, nowhere in here are we changing vec, this should be const as well. Okay. And so remember the rule of thumb. Just like 90% true, I would say. Primitives like ints, doubles, floats, etc. pass by value. Big things, super technical, like strings and now vecs are called by reference. For what you should do by default, I guess is the best way of putting it. Like sometimes you'll need to pass an integer by reference. Why? Because you want to change it. You know, but like if you just don't know what you want to do, by default an int should be passed by value and a vector should be passed by reference. And usually const reference. Okay. So by default, if I ever pass a string to a function, I'm going to pass it const reference. If I ever pass a vector to a function, I pass it by const reference. Until like I decide, oh wait, I need to change this, like I need to delete things out of it or something, then it won't be const anymore. But yeah, that's the rule of thumb for that kind of stuff. So let's see what it looks like if we wanted to do this with an array, C++ array or C array. We'll do both. mx y single quote x shift p open for O, pass in a C++ style array to a function. And so for this one, we're going to be passing in an array of integers of size 5, specifically size 5, which is kind of annoying. There's a better way of doing it, but you'll learn that in C/41. And so that's basically how you do it with the C++ style array. C++ style arrays are just better versions of C style arrays. This is kind of annoying though, where you have to hard code the size into it. Like I said, there's a better way of doing it. But you don't really need to worry about C++ style arrays either, because you should use vectors for everything in this class. And then this is how you pass a C style array to a function. And there's going to be one very important twist here, which is that you do not pass it by reference. You do that. Okay? Note, you do not pass it by reference since an array is a reference. So all an array is, if you like looked at your RAM, all an array is the memory address where the array begins. And so that's when you pass this in like that it's passing in the beginning of the chunk of RAM that it corresponds to. When you pass in the vector like this, it passes in the beginning of the chunk of RAM the vector corresponds to. And that's actually just what an array is. So technically an array is a primitive. So primitives like ints, floats, doubles And arrays, they're built into the language, right? Call by value. Okay. So yeah, an array gets passed in like that. Notice this code is not compiling. Why? Here it compiled, right? And we had a range-based for loop down here for every integer in R. See out that integer. It worked here. Why doesn't it work here? I told you the answer to it earlier in the lecture. Looks the same. Why doesn't it work? Anyone remember from half an hour ago? What happens when you pass an array to a function? Anyone? Can you still tell the size of the array once you pass it to a function? Size goes poof. That is exactly right. Graduate of the computer science program here. Yeah, so anytime you pass a C-style array to a function, you have to pass the size in also. And you can't use range-based for loops anymore. So you got to do it the old-fashioned way. Size ti equals 0, I is less than size, I plus plus. If r sub I is less than 100, count plus plus. So, note, with C-style arrays, you have to pass the size in. And that's another downside to it, because if you get that wrong, which does happen if you have a bunch of arrays and a bunch of sizes, and you're copying and pasting things, you will get the size wrong at some point, then you'll buffer overflow, because this code does not know how big R is. When you pass R to this function, it knows where the beginning of the array is. It does not know where the end of the array is. That's different from this. Because you're passing in 5, you know where the beginning of R is on this one, and you know where the end is. And with vector's got dot size, right? So you know where the beginning is, you know where the end is. With a C-style array, you only know where the beginning is. And so you have to pass in the size separately and hope they match. Arrays seem like a huge pain. Yes, don't use them. Cool. All right. If you can summarize today's lecture in one sentence, don't use arrays. Okay. Yep. So this is 3 different versions of 3 different containers. This is a vector of integers. This is a C-style array. This is a C++ style array. And for this class, you just want to use this one. Rant over. Let's now talk about sorting a vector. Okay. So what does it mean to sort something? It means you want to make it organized, like when you sort a deck of cards. You know, you have the smaller numbers first, going up to the bigger numbers, right? So sorting is one of those things that can be done badly quite easily. So let's sort a vector. Let's not worry about the other ones. So we call this one stupid sort. And we're going to take in a vector of integers named vec by reference. And we're going to sort it. We're going to put them in order. So the smallest numbers are going to be first. The biggest numbers are going to be last. And why is this not const reference? So the vector knows the size just by the values in the curly braces. Yep. This is called an initializer list. And the initializer list actually has size information baked into it. So it actually copies its size from the size of the initializer list. I wonder if... I don't think that would work, but yeah. I don't think you can access it directly, but you can... yeah. Because we're changing the contents of the vector. Exactly right. So we can't make it const reference. Like I said, it's going to either be reference or const reference, and it just depends on whether or not you're going to modify the vector or not. In this case, we're sorting it. Okay. So, because it's going to change the position numbers are held in. Yep, that's exactly right. We're going to be moving it around. So, let's start off with a for loop, and for this one, we're going to do a regular for loop, because the indices are actually going to matter a little bit. So let's say that we've got these numbers here. How would you go about sorting these things from least to greatest? There's a lot of different approaches here, and it kind of randomly shuffle them until they're in order. I like that. Okay, so we can call random shuffle back dot begin back dot end is sorted back. Random shuffle is a function actually. You gonna do bubble sort? Okay, sure. Let's do bubble sort using the greater than or less than operators. Yeah. So yeah, let's do bubble sort. So the way bubble sort works is you kind of start at the beginning, starting at 40, and you look at the person to its right, 10, and you're like, is 10 smaller than me? If it is, swap them. Okay, so it'll swap 10 and 40. Then it goes on to the next comparison. So it's going to compare 40 and 20. Is the person to my right smaller than me? Yep. Okay, swap them. So that becomes 40, that becomes 20. Check the person to my right. Is it smaller than me? Nope. Then don't swap them. Then last one, check 60 and 5. If they're out of order, which they are, swap them. And we're done. It's sorted now, right? Not quite. It's more sorted. So how many times would we have to do this operation to get 5 to bubble up to the front? How many times would we have to loop over the whole thing to get 5 if it's swapping up once per loop? Yeah, we're gonna have to do this size times. So let's make a doubly nested for loop. All right, and so if vector dot at j is, so if we're currently at 0, so if our value is greater than the value of the one to our right, vector dot at I plus 1, then swap our values. Swap is a function. Vector dot at I, vector dot at I plus 1. There. Almost correct. Almost correct code. There's one small wee little problem. Anyone see it? 2, 3. There's 3 problems. Sorry. I built them all intentionally into the code to see if you could find them. Like I said, I don't write bugs. Just happy little accidents. Is there a sort function? Yes, there is, and I'll show that in a second because that's way easier to write. Nobody wants to write this themselves. Remember, if you guys don't want to write bugs, that's my, like, you know, here's learning point 2. 2 for today is that don't write bugs. Right? So remember that lesson, okay? So just don't write bugs. It'll make your computer science experience much better. Okay. I know, it is. If you guys can follow that advice, you'll do very well in computer science. Swap is a function. Yeah, swap switches the values of 2 variables. All right. If you don't know how to do that, of course, you say if bug don't. There you go. That's a very important line of code right there. You're going out of bounds? Yeah, we're going out of bounds. Yeah, except it shouldn't be I, it should be J, right? Because this is the inner loop. So these should all be J's like that. And so we're comparing the value of the current person to the person to the right. When we get to 5, because we're going to the end of the vector, it's going to try comparing the value of 5 to the value to the right of 5, and that will crash. So if we try running this, if we try running this, it's going to go out of bounds. Okay, so we're going to print the vector, we're going to sort it, and then we're going to print it again, except it's not going to work because we're going to go out of bounds, and there we go. Okay. And so whenever I am writing code and I write dot at person to my right, person plus 1, the first thing I do is I immediately come up here and say, don't go to the last element in the vector. If I check the value 2 to the right, then I stop 2 to the left. You know what I mean? If I'm going to access people 5 to the right, I stop 5 away from the edge. Okay? So that's a good rule of thumb for you all to practice, is that anytime you're checking values to the right, and contrast if you're checking values to the left, like if you did this the other way, like j minus 1, then you'd have to start at 1. And if you're checking at j minus 5, start at 5, right? And so anytime you're playing games with the indices like that, immediately pull in your for loop. Okay? Yeah, so this code should work. Let's see here. All right, there we go. So it is now sorting the numbers from least to greatest. So that explanation was pretty minimal of what I was doing here. But basically what it's going to do is it's going to run over the loop. It's going to loop over the vector. And for each pair of numbers, if let's say j is 0 to begin with, if j is 0 to begin with, then it's going to compare 0 and 1. Since 0 is greater than 1, swaps their values. It then compares the next two, and since 40 is greater than 20, it swaps the values. 40 is not greater than 60, so it does not swap the values.
0 is greater than 1.
0 is not greater than 1. I don't know what I said. Okay. Oh, the person at spot 0 is bigger than the person at spot 1. Okay. And then we've done it 1 time. Now we have to do this 5 times. So we have to keep doing it. We could bail out early if we detected no swaps were made. That would be a neat little optimization. But basically, because it's going to take 5 times to get that last person up to the front, we have to do it 5 times. So this loop here, make sure 5 will bubble up to the front. And then this one, swap people out of order. With the neighbor to their right, I guess. So this is called bubble sort. It's a slightly worse version of bubble sort, in fact, because real bubble sort will remember if it didn't make any swaps, and so it can stop early. So if you pass regular bubble sort, a sorted array, it goes through it. It's like, I didn't make any swaps, done. So it's actually faster than my implementation here. But either way, this is a dumb way of doing sorting, right? So the correct way of doing sorting, incidentally, let me show you. Rather than that, there is a function called sort. And sort takes 2 parameters, where to begin in the vector and where to end in the vector. Okay. And so this is how you sort. Learning point number 4. Okay. There you go. That's a very important function. You should pay attention to it. Sort sorts from lowest to highest by default, yeah. And if you're asking how you can sort from greatest to smallest, you can pass in a 3rd parameter here that tells it how to sort. And you can look that up on CPP reference. Okay, so So the final point that I wanted to make here, oh, that was learning point 2. Now that's really learning point 3. Not learning point 3. Learning point 2 is how to pass things to the functions. Learning point 1 was the pros and cons. Pros and cons, learning point 1. Learning point 2, how to pass them how to pass vectors and arrays to functions. Learning point 3, don't write bugs. Remember, if you're ever getting into trouble with bugs, just say if bug don't. Then all your bugs will go away. It'll be amazing. And then finally, learning point 4 is you can sort by just doing that. But we're out of time, but here's the question. If I had 1,000,000 people in the vector, how many times, possibly, what's the worst case scenario for this? How many times might it do a swap? If vector.size is 1,000,000, how many times might it do a swap? How many times will it run? How many iterations do we have? These are all kind of equivalent ways of saying the same thing. If vec was 1,000,000 in size, how many operations must we do about? 2,000,000? So 1,000,000 times we're going to be doing this outer loop. For each one of those outer loops, we're going to be doing 1,000,000 of the inner loops. So it's 1,000,000 squared, which is a trillion, right? It's 1,000 billion. Although if you're British, that might confuse you because they use billion in a different sense of the word, I think. So, yeah. So bubble sort does, it would be 1 trillion. What if you had n? Let's just make this more general. N elements. How many operations does this algorithm do? What do you think? So just generalizing this, if we have 10, n is 10. If we have 1,000 elements, n is 1,000. How many operations does this do? And there's a -1 in there somewhere, which doesn't matter. We round these things off. N squared, yes. So we call this an order n squared algorithm. So the running time of the algorithm goes up with the square of the inputs. Now, what is the running time? Boolean sort. What is the running time of sort from the standard library? It's order n times the log base 2 of n. So how fast is that? Well, a lot of people don't have an intuition about logarithm. So let's open up the calculator and see. So if we had 1,000,000 names in like a phone book and we're going to sort it using bubble sort, 1,000,000 times 1,000,000 is a trillion. We've got a CPU that runs 4 billion times per second. So it will take 250 seconds to sort our phone book of names. Potentially more because strings are actually quite annoying to work with. So let's actually multiply it by a factor of, whatever. Let's just say 250 seconds. So divided by 60, that is 4¼ minutes, or thereabouts. Okay, a little bit over 4 minutes to sort 1,000,000 names, which isn't even that many names if you think about it. Like Fresno's metropolitan area isn't that big, you know, and it would take 4 minutes to sort it to make a phone book or something. If we're using the standard library sort, by contrast, it would take, what is the log base 2 of 1,000,000? 1,000,000 log base 2 of 1,000,000 is about 20. Oops. 1,000,000 log base 2. No, what is going on here? It's like times 0. Okay, it's 20. I'll just tell you the answer. So 20 million divided by 4 billion operations per second is 0.05 seconds. So if you use bubble sort, it takes 4 minutes. If you have the standard library sort, it takes approximately 1/200th of a second. Guys see the difference? Substantially faster to have a order login sort versus order n squared sort. How does it do it? Don't know. Doesn't matter. There's a number of algorithms that run at that running time of, what's it called, linear logarithmic or something like that. There's merge sort, quick sort, heap sort. There's a lot of algorithms that actually run in order n log n time. Most standard libraries use quick sort, but that's a topic for another day. So there's a lot of different sorts that are all optimal. And so what they do is they benchmark them on different architectures and find out which ones are fastest in practice. But in general, they're going to be all order n log n. So they take roughly 20 million operations to sort a million names, rather than a trillion. 20 million, a trillion. 20 million for standard sort, for the standard library sort, a trillion for this one. That's why I call it stupid sort. Okay, so that's this kind of stuff here, this algorithmic analysis, figuring out what's faster than another one, is a topic we cover in depth in CSI 41. But this kind of gives you an idea of, like, do these things matter? Yeah. Yeah, 4 minutes is like too long for like interactive programs, but at 200th of a second, it's fine. Yeah. Or you do stall and sort, where you shoot anybody who's out of order. Mr. Bell's idea of shuffling until you randomly get it right. Yeah, there's a lot of algorithms out there, but that's enough for today. So, any questions about Mandarin? Mandarin is due on Friday. Just ask them after class right now. Any questions about this? Just ask. Okay. I think we'll stop here and pick it up again on Friday. All right. See you guys.